Hi everyone. I'm Sundareshwar, and today I'll be your host for the monthly seminar on the topic of an overview on Bpftrace. Um, it's a Linux tracer that analyzes production performance problems and also troubleshoots software. It helps you troubleshoot software. So, at the start, what is Bpftrace? Well, it is a high-level tracing language that allows you to write scripts to instrument and trace other programs. It is mainly used to gather data on the behavior of programs running on Linux system, and is particularly useful for analyzing and troubleshooting various issues. So you might ask, like, what type of high language it is. So the syntax is bit similar to C. I'll show you in a bit. So the syntax is similar to C, and it is using BPF, that is Berkeley Packet Filter, in the Linux kernel, which was basically developed to trace to filter network packets, but now it has been expanded to trace such as kernel probes and trace points. And from BPF, many user space tools have been developed, such as Bpftrace, and which helps us developers to write and test and deploy various BPF programs in a user friendly way. So, a couple of points for it. So, mainly the users and contributors were Netflix, Facebook, Red Hat, and it was developed by a UK based developer called Alistair Robertson. So, and yes, so well, Linux has it already has many performance tools, but the main issue that arises is some of them are either counter based or have limited visibility. For example, let's say IOStat or any other monitoring agent may tell you the average disk latency of a disk, but sometimes it may not be the solution of an issue. You might need to see the whole distribution of the latency. So sometimes there's some blind spots through which you need to see which can be detected from average. Through this BPFT trace, we can use for this kind of analysis, like decomposing metrics into distributions or per event logs, and creating new metrics for visibility into those particular blind spots. And yes, you can use BPFT trace via one-liners from the terminal, or you can create a script and trigger using the BPFT trace command. So here's the syntax. So normally, BPFT trace, you can start using, like, you can attach a probe, then you can give a filter and an action. What is a probe? Well, a probe specifies what type events to instrument. There are multiple of probes, for example, K probe, taste points, U probe. Um, there are multiple things. I'll show you in the next slides. But from using that probe and attaching it to a function, you can specify the action of what kind of thing that you want to do. Let's say the basic hello world program. So let's see, BPFT trace -e will use begin. Begin is the probe here, and the action would be printf hello eppf. Well, begin is nothing but it would be triggered when BPFT trace is just been started. So it will be something like beginning of the program. So we just wanted to be like at the beginning of the BPFT trace program, we'll just print hello eppf. Now, if we go to deeper, so let's say BPFT trace -e, e means execute. So K RAT probe. What is KRAT probe? It's a kernel probe which has been triggered when the function is being returned. So I'll again explain this in a detail, but for the sake of understanding, it would be something. This probe has been attached to a function called sysread, and it will be tracing the process of 181. So what does this do? It allows, so let's say the K probe, KRAT probe is attached to the sysread function, and there's a histogram called bytes. When the probe is hit, like when the system read function is called by this particular process, the bytes will be, let's say, will be recorded in this histogram. So this script normally allows you to track the number of bytes read by the sysread function for each call and create a histogram for the values. So moving on to the next slide. So here's an example which will go now in the detail. So let's see, here's is in this one liner, or let's say a BPFT script. What we do is we are reading latency between start of the function and the return of the function, and we'll then print the latency between those calls as an histogram. So we'll this Bpftrace script uses kprobe and kret probe. Kprobe is a specific type of probe that can be attached to a function or a kernel function, allowing it to hit or perform a custom action when the probe has been hit. So, and kret probe is similar to kprobe, but this will be triggered only when the function is being returned. So kprobe will be hit when this VFS read will be started, and kret probe will be hit when it's the particular function is being returned. So in this script, the kprobe is attached to a VFS underscore read function, and will create a histogram namings as start. And for each thread TID, so TID is an inbuilt function which has the thread of the or the thread ID of the function head. So we'll attach it to the at the start histogram. When the probe is hit, the current time will be recorded in nanoseconds to this particular variable. And when and we go by going to the next line, it will be kret probe. And when the function will be returned, the same and another histogram will be created named ns. What we will do is we'll minus the time between the start of the function that we added that we recorded here and the return function time. So what this will have the difference between the nanoseconds of between the start of the function and the return of the function. And we'll, for the sake of the next function hit, we'll just clear the data now. And this will be tracking until we control C it or command C it back out of the function script. So after recording each function hits, it will display a histogram. The histogram might be confusing at the first, but we can see it will contain each line. The histogram represents the range of the durations and the number of occurrences of the function that falls in that range. For example, let's say the first line indicates 10,900 occurrences of the function calls that lasted between 256 to 512 nanoseconds. So this will show if there's an let's say if the as there most of the calls or the occurrences are within the 1000 nanosecond, it's fine. The function seems to read fine. But let's say what if there are many type of occurrences in 16K to 32,000K nanoseconds. That means there's a problem between the read function. It is taking too much time to get the function completed. So this is how we'll be able to find if there are any discrepancies during the read latency. This example instruments one event of the thousands of available functions in Bpftrace. If you have some weird performance problem, there's probably similar one-liners that will shed light on the later part. For example, let's say in large environments, this ability can help you save millions. For small environments, it will be more helpful to reduce those latency outliners. Moving on. Let's say so these are the probe types that we'll be using. Let's say first there are multiple of them. One is trace point. This is I think the most commonly would be the trace point and k probe. Well, trace point is a type of probe that allows you to trace the execution of specific kernel functions or other events. There are many predefined locations in the kernel, and it already has many type functions in it. Well, the data will be handled through it. The data can include information about arguments passing to the function, the current CPU process, other relevant context, and coming to kprobe, the instruments beginning. Well, as previously we saw in here, it will be triggered when a kernel function is being called at the start, and same goes to the kret probe when it will be called when the function that is tracking is being returned. Same goes to a U probe and U term, but it's not a kernel, but it's related to user level function. These software and hardware related to kernel-based software events, and this will be related to hardware events. These are watch points. Memory watch points are nothing but whenever a memory address is returned, read, or executed, this kernel event generates those events. And profile and interval would be used if we want to see the performance related to a CPU core or a thread. And begin and are just a common functions that we want to run if we want during the beginning and ending of the BPFT trace script. So these are the variable types that we can use in BPFT trace. We can store data in them temporarily during the execution of the script. So at the rate name would be globally defined, and at the rate name, if you specify a key or a thread, it will be local to that specific thread or the key. And this would and hash scratch would be nothing but a specific, if you are losing a in the action, it would be specifically to that only. So we can assign them, normally that we do, like at the rate name equals to x, or at the rate name equal, or can also assign a function to it. And there are some built-in variables which we cannot use, of course, but we can already get the data from them. Let's say if we use PID in any of these variable definitions, we will get the process ID of the particular process. If you want to get the let's say the process name, we can use comp. If you want to get the current time in nanoseconds, we'll use nsecs. If you want to specify the kernel stack trace, we'll use kstack. Same goes to ustack. And if you want to get let's say the function has a couple of arguments, or we want to take arguments, we'll use uh, this type of syntaxes. And there are a couple of let's say the args for the trace points, and the function return values will be called as retval. So when anytime, let's say, a function is returning a value, not here, but when the function if the function returns a value, we'll use retval for to get the specific function value, and we'll use name to get the probe's name from there. And there are also a couple of functions that we'll be using. One is, of course, printf in Bpftrace, which follows the exact same syntax as C. We can use %d, %s for the formatting of it. This will be time. We can define it by using %h, %m, or something like that. And if you use system function, you can directly run shell commands in Bpftrace by using this. And if you want to count specific events, you can use this. And if you want to create a histogram, you can use this type of function. And you can also create a linear histogram by using directly this. You can directly create a one line of histogram. So, so these are a couple of examples that we'll go through today. But before going through all those one-liners, I'll just show you a small, let's say, an example of a simple example through which we'll just see, let's say, if I'm writing a command in this terminal. Let's say if I want to cat, what anything is here. We wanted to like cat test.json, right? Um, I'm running a couple of commands. I might make a directory called test. But what if I wanted to track all these commands? So we can write a simple BPFT trace script or one liner through which we can track the commands being ran on the bash terminal. So for that, we'll use BPFT trace, and we need to always use -e that specifies that we need to execute the specific line. We'll use single quote, and as bash is a user level process, we'll use the probe, and we want to trigger this when the function is being returned. So we'll use uret probe, and we'll specify what function we want to test. That is, we need to track bin bash, and we'll let it read the line of bin bash. And we also want it to be in a specific format, right? So we'll use the action brackets. We'll keep the action brackets, and we'll just place the time function, and we'll format the time function as %r, and we'll I'll give it the minutes and the seconds in which the line has been written. And also print f the let's say we'll also print apart from the time of the command being ran, we'll also print let's say the PID of the process, and uh, let's say what command that has been run at that time. So I'll just create a space between those two. And also, yes, we'll specify how much maximum we need the PID to be. And and percentage string for the let's for the string that we're going for the command ran for that the command ran string. So that's done. I'll keep the PID here and I'll like let's say return we need to get the return value, but we'll convert it as a string format. So this would be basic uh, command that that we are being written. We'll also close this. That's it. Should probably run. Yes. One thing that we need to note is Bpftrace always support like only runs on as a root user. So you need to always specify either just go to you just sudo it, or you can always use this sudo command along with it. So just use sudo command type of command. And right now it is showing attach one probe. So now this probe has been attached. The ureturn probe will be attached, and it's tracking the commands that were being ran from here. So let's just clear this out. So let's say I'm using ls-la. I have catted test.json, and I have also created a make directory of test one folder. So I have ran three commands. One is ls-la, and the catted.json, and I also created a directory from it. So as you can see, it tracked, I think we missed a space here, but it tracked all of those commands. It tracked the seconds at the time when the command was executed, and also the PID, also the process PID from where it has been executed, and the exact command of what has been executed there. So this is a simple Bpftrace one-liner that we have used to track different commands, or like the bash commands that are being there. So if I wanted to explain this in detail, um, so this is the probe point that is being attached. URET probe is a type of probe that is being triggered when the user space function returns, and this probe is attached to a readline function with the bin bash executable. Of course, after attaching the probe, you need to specify the action as well. So I'm opening the bracket of action, and this is a function time, and which also prints the time function time as a string, but we also specify what type of like what formatting do you want. Once that's done, I have given a printf function in which I have specified the process that I need to the process ID, and the return value or return value would be the string that the command has been using. So when the read line function of the bin bash is executable returns, the probe is triggered, and the script disk block is executed, and the process, the current time, and the command that was executed will be printed here. And yes, but if you want to like try to run this in your own Bpftrace like the terminal, make sure that just use bash terminal. So that's a basic BPFT one-liner, but there are multiple of them. So we'll go one by one, and also once we get into the complex territory, I have another example that we could perform here. So one would be listing probes. So so every kernel has different type of probes. So each computer has different kernel. So each kernel has different type of probes. So if you wanted to see what type of probes that you have in your computer or your machine, you can always use bpftrace -l to list out the specific probes you want, and you can also like filter out using single quote and entering those specific string, and you can use star to get that specific trace points. So let's say in here the user wants to like gets the syscall trace point group. He wants to go into the syscall trace point group, and he enters sys underscore enter underscore star. So it will print out all the trace point that has the same pattern of sys underscore enter a star. And by running this command, you'll able to see the trace points in the syscall group through which you can call various system call events that are running in the kernel. So that was the listing part. And let's say previously we saw how we could trace the commands from a bash terminal, right? So now another let's say a script or a one-liner is how we could track when a file opens. So when a file has been called or opened, generally the sys underscore open system call will be triggered. So the trace point syscalls sys underscore enter underscore open will be triggered. So the script generally defines a block of code to execute when the trace point is hit. The block uh, the block contains a print statement. It has the process name, which from which this function is particular function is being called, and it will also get the file name from it. So let's say when I trigger a system call, it will print out the function name, it is the process name which has been calling, and it will get the file name from the arguments of sys enter underscore enter dot open. So we can get the real time processes. We can see if in real time when the process calling an open file calls from the system. And this is another example. Sys call counts by process. So this has um, system call called sys enter. So normally this uses the count function. It just counts the uh, number of times that this call is being called by process. So we are creating an array called COMM, and we're creating an array with the process name attached to it, and we'll count it. So COMM is the built-in variable to get the process name. So when a particular process calls a sys enter, it will count. It will increment the count one by one. It will get the values, and it will in the end will print out the values. How many like different private process called the system underscore enter, like an amount of times. Um, so I have another example that I wanted to show. Hmm, we can do after this. Yes. So there's also we can also use this Bpftrace to distribute like to see how many to see the histogram of read bytes. So in the start of the presentation, there was an example. It's the similar example. So if you wanted to see how many read bytes are being used for the exit, like whenever a process exits, we wanted to see how many bytes have been like read by the particular process. We can use this particular script. Well, it defines a histogram called bytes and a block of code. It will be executed when this particular trace point is being called. What it does, it records a system underscore read value in bytes, and it will copy it to the histogram. And when BPFT trace exits, it will show you how many bytes are being read by the system read call. By if you want, let's say, if you want to track process, we can specify the process, or it will print out all the processes. So it will be useful to see the read behavior of specific process or identify process which are reading a large amount of data. Another example that I wanted to show is this. So let's say if you wanted to trace a process, let's say how many like a process, if any process requesting a IO request, or it requesting to block IO request by the kernel, right? So I'll just be starting like, let's say ppft trace hyphen e. Um, for this we'll be using trace point, um, and we'll be using the block call functions. So we'll use the block call, and in the block call we want the block call request issue. So we'll do that. And for the action, when this call has been triggered, we want it to print the PID, and let's say the process name and the number of bytes that it wants to request it. So for the process name, it will be string, and for the bytes, it will be integer. So slash n, the new line, and let's say this will be the com would be always the process name, and uh, we'll get the number of bytes requested from the arguments of the function. So we'll convert into we'll get it from bytes. So what if now if I run this, Mm, I forgot that. There you go. So now it's tracking number of, so yeah, so there you go. So a couple of processes requested these kinds of number of bytes from the IO from the kernel, these kinds of bytes of IO request. So it's showing the number of bytes requested from here. What if I wanted to see the PID of it? So it's simple. So I'll just add the percentage D here to get the PID of it. So let's say there you go. Now it's also giving out the PID, process name, and the number of bytes requested. So let's go into detail. Where is it? Yes. So this trace point is being attached to the block request issue trace point, and this trace point is triggered when the block IO request is issued by the kernel. When the probe is triggered, the script will execute this printf statement. Um, which has the PID, com, and arguments, right? And com will be the name of the process, and this function has a built-in uh, has a specific structure of arguments, so from which we'll get the bytes of it. Well, this command is always useful to trace the IO activity of certain process, and we can also see the IO pattern of the system. With this information, you can see which process is doing a lot of IO and which process has a large IO request. We can also count this, and we can change the modify the data to the required analysis we want. So that would be another example. Going back to the one-liners. Yes. So moving on. So how so this was the distribution of the read byte from the system call, right? So we can also use this one for tracing the kernel read bytes. This script allows you to see the number of bytes read by a VFS read function, and it will create an histogram. Mainly, it's useful to understand the read behavior of a program and the patterns or the trends in the data. So what it has a caret probe, which is a probe which gets triggered in the when the function returns. And what it does is it creates a histogram named bytes, and when the probe is hit, the block creates a histogram um, which has the written value from the VFS read function, and it will have the minimum value, the maximum value, and the number of logarithmic intervals. For us, we just gave it 200. So it will read the number of it will give out the number of bytes read by the VFS read function using this Bpftrace one-liner. And this is another script which gives out how much time the process is spending in the VFS read function. Um, so initially it will read into the it will initially when the function has been triggered, it will get the time, it will note the time, and when the function returns, it will minus the time and get the output. So this much time has been spent by the VFS. This is the same function that we use in the example, so I'm just skipping it. So the next would be count process level events. This script the script allows you to see how many times each trace point of uh, schedule or SCHED function has been called, group has been hit, and it will run. And we can also set an interval. So this 5 seconds in this one liner, we have kept the interval as 5 seconds. So this BPFT trace will run for 5 seconds, and it will eventually exit it by giving out the data. So what happens is it will trace all the trace points that has the same pattern of the sketch group, and counts the number of times each trace point is hit. The script also sets up an interval which will be exited after 5 seconds. Um, well, what it does is yes, it will see how many times this has been called, function has been called, and it will eventually exit it. The other is using the profile function. Profile is a simple probe which is generally used to see to track any CPU events. And so for that, we use the uh, profile probe, and we'll set the sampling rate to 99 hertz. Um, and we'll just count the number of stack trays being sampled. So it will just sample the number of let's say um, it will just sample the number of calls it will, like, let's say, okay, I'll get back to it. So this block of code just increments the counter for the stack kernel stack trace stack. In the array name stack will just print out the kernel stack traces. So this script allows normally to see the kernel functions which are being executed the most and can be useful to understand the behavior of a program, or if you want to identify any issues. As a sampling rate is 99 times, so it will always check constantly. Um, so this is a scheduler tracer. What it does, it will look for the scheduling switch trace point. It will count how many times the process does the context switch between them. So we can also use this Bpftrace one liner to see if how many times the scheduler is changing the processes between sleeping and running. And this is the same as the example. It will just trace how many times the block request issue has been called, and it will show how many bytes has been requested from it. Yes, so for now, until now, we have seen one-liners for the Bpftrace. So we can also provide a particular script to it with the extension .bt. So for example, let's say Bpftrace path.bt, where the path.bt contains these lines. So we can also specify the scripts in this format. In this script, there's a block of code which defines when the file is being opened. It will show the path of the file where the file has been opened, and also yes, and also when the file is in the path. Yes, it will just show the path of the file where, let's say, if a program calls a specific path in the home directory, it will just print out the path of the home directory. It will constantly do it until we exit it. So for that, so the reason that user has been using this a script here, that because we need to specify, as we are checking the path, as we're getting the path from here, we need to include the path.h library file to in order to Bpftrace to work. So that's the reason we are using a script to get the path from it. So those were the one-liners and the script. So if you go to the repository of Bpftrace, there are multiple tools for multiple use cases. For if you want to check for file systems, I think XFT test is one of them. And if you want to track any TCP related issues, there are multiple scripts called TCP accept, TCP connect, which have a particular use case. And the most that we have been using were, of course, block device, which has biosnoop, biolatency, and byte size. Which biolatency is the same script which tracks the difference between the read and writes of latency. Um, so these are the multiple tools that we have. You can check the code in the repo. I have given the reference links in the last. So from all those tools, I'll just explain one of the tool that I have, the most common one that I've been using. And yes, this is the first script that I've learned from myself. So this is a script in the tools folder called biolatency. This BPFT program traces I/O input and output block operations on the block devices such as hard drives and SSDs. So it normally traces using the block account IO start and a block account IO done. So what it does, so at the start, so it has four sections. So I'll go one by one. So at the first section, the begin block, this is ran when the BPFT tracing will be executed. So it will just print out a simple statement called that I'm tracing block device IO, and you can end the script by hitting Control C. So after the begin done, it will attach the probe called block account IO start, and it will copy the seconds, or the copy the exact time of a particular block IO when the let's say when the this function is particular called this function is being called. It will record the particular time and the function the function that the block device, that the identifier of the block device where the operation is going to occur will be recorded with the time with it. And with the block account IO done is executed when the function throws that yes, I have uh, completed using the block IO. Like now you can release the block IO. So at the so it will record in the start will record the number of time, the seconds of the call, and the end when this function has been hidden, it will minus the nanoseconds from where it was been started and where it has been done, and it will create a histogram called @usex from it. And in the end, when we hit Control C, it will give out this type of histogram. It is the same as we saw previously. The number of occurrences, like let's say for the second line, 10 times the block request has been completed within 512 to 1000 nanoseconds, and 426 times the request has been completed between 1000 to 2000 number of seconds. And yes, we can microsecond. So, so yes, so those are the Bpftrace introduction, and we can also find these references that I took from these links. And another thing, if you want to go a lot deeper into each functions, each probes, I'll add this and I'll add this link in here. So if you go to the repo, um, this is a reference guide of it. So if you go to the Bpftrace repo, you can go to the docs and you can go to reference guide. Each and every function, each and every probe is being explained in a very detailed form of manner. Let's say if you wanted to learn what is kprobe, if you go click here, it will show the examples where the kprobe can be used, and to also explain in detail of each and every function. So yes, so this is also a reference guide if you want to go dig deeper into the Bpftrace tool. So yep, that would be probably from my side. Thank you. And yes, if you have any questions, please.